Alright, this video is going to be on differential equations. So first we're going to start off defining what a differential equation is. And it's an equation that contains an unknown function and some of its derivatives. So when we look at differential equations, they have different orders. And the order of the differential equation is determined by the highest order of derivative that occurs within that equation. So for example, if you had y prime equals xy, y prime is the derivative that shows up in this differential equation, and y would represent some unknown function. And here we would say this is a first order differential equation because you only have the first derivative in there. If you had xy plus y double prime equals 1, you have a second derivative in this differential equation, and so that would be a second order differential equation. If you had 2x plus 3y triple prime equals y triple prime, you would say that this is a third order differential equation because it has a third derivative in it, and so on. So we'll do a few examples in the video of how to work with these, and then I'll leave a few examples for class as well. So first, we're going to say that we want to find a function whose derivative is a constant multiple of itself. So if I was to write this out just with notation first and then think about it to see if I can find a solution, I would say that this means that y prime is the same as c times y, where c is just some constant. So it could be like the number 2 or the number 5 or something like that. So a good example of a function whose derivative is just a constant multiple of itself would be e to the x. So if we think about e to the kx, where k is just some number, then when I go and find the derivative of that, I'm going to say y prime is e to the kx times k, using the chain rule there. And so if we simplify that, we typically put those coefficients in the front. And so that's k times e to the kx. So we can say that the derivative of the function is just the original function with a constant in front of it, a constant multiple. For the second example, we're going to find a function whose second derivative is the negative of itself. So for this, the differential equation that we're looking at would be y double prime equals negative y. And there are two functions that would actually do that, and one is y equals sine x, and the other is y equals cosine x. So if you think this through, the first derivative of sine is cosine, And then the second derivative of sine would be the derivative of cosine, which is negative sine. So if you're comparing the original function with its second derivative, it's the negative version of the original function. And it would do the same if you started with cosine. So the first derivative of that is negative sine of x. And then if you take the second derivative, that would give you negative cosine of x. So the same thing. The second derivative is the negative of the original function. All right, next we're going to look at three different functions, and we're going to determine if any of them are a solution to this differential equation. So determine whether the function is a solution to y double prime minus y equals 0. So we want to know if we take these functions, if you take their second derivative and subtract it from the original function, if they would cancel each other out. So the first function we're going to look at is y equals sine of x. And we just went through this set of derivatives. So I know the first derivative is cos, and I know the second derivative is negative sine. And if you say the second derivative, subtract the first derivative, in this case it would not equal 0. And so I would say no. The function y equals sine x would not be a solution to that differential equation. So for our second function, we're going to look at y equals 4e to the negative x. So if you take the first derivative of this one, that would give you 4e to the negative x, and you'd have to multiply it by negative 1 because that's the chain rule. And so that would simplify to be negative 4e to the negative x. And then if you take the second derivative, we're going to start off with this, and we have to do the chain rule again. And so these two negatives would cancel out, and we would get back to positive 4e to the negative x. So if we look at that original differential equation that we were solving, it was y double prime minus y equals 0. So y double prime is 4e to the negative x, and you're subtracting off 4e to the negative x. And since those are the same, they cancel each other out, and we would say yes. That is a solution to the differential equation. And then we'll go ahead and do one more example. We're going to say that our function is ce to the x. So if we look at this one, the first derivative, whenever you take the derivative of e to the x, you just get e to the x, and the constant stays in the front. So the first derivative of ce to the x would also be ce to the x. And you can think about doing the chain rule, but the derivative of that exponent is just 1. So that doesn't change this equation at all. It keeps it the same. And then the second derivative would also be ce to the x. In fact, if you kept doing derivatives forever, they would always be the same thing. So if we look at this differential equation and we do y double prime minus y, it's going to equal 0, and those two things are going to cancel each other out. Okay, we'll do one last one and then call it good. So we're going to verify that y equals cx to the third is a solution of the differential equation x y prime minus 3y equals 0. And then after we verify that that's a solution, we're going to find the particular solution when y of negative 3 equals 2. And this is kind of like function notation where you say f of x and you're giving the x value to plug in. So this is just, instead of saying f of x equals, we're saying y equals, and we're going to plug in that negative 3. So if you look at your differential equation, we already know what y is, and so this y is going to be plugged in for y right here. But right here we have a y prime, and we have to know what that is so we can plug it in. So I'm going to take the original function and find the derivative of it. So that's going to give me 3cx squared. So I just took the exponent and brought it to the front and dropped it by 1. And then I can go ahead and plug it in. So I've got x times y prime minus 3 times y and if I multiply this together, that gives me 3cx to the third, and this gives me 3cx to the third. And so when I subtract those, they do equal 0. So we just proved that it was a solution. And now if I want to find that particular solution, when you plug in -3 for x, that's going to give me c times -3 to the third power equals 2. So I'm plugging -3 in for x, and I know that the y value there equals 2. So this is c times -27 equals 2. And that means that my c value at that particular instant would be -2/27. So that equation, that's a solution for the differential equation at that point, would be y equals -2/27 x to the third.